Hello everyone, I'm Robert An, a PhD student at UT Dallas, working with my colleagues Sam, Ronaldo, Diana, Lipping, Tom, and Lawrence Chong. Albert Einstein said the mere formulation of problem is often far more essential than its solution. Here, Einstein emphasized the importance of problem formulation. Our work is similar in that we focus on problems, especially validating hypotheses of these problems. Today, we'll present our work validating goal-oriented hypotheses of these problems using machine learning. Here is the agenda. First, we will introduce motivation of our work. Next, Metis method for validating problem hypotheses. Then experimental result, and lastly conclusion and future work. From a business perspective, appropriate use of machine learning seems to be a challenging work. New technologies such as social network services, videos, and sensors are collecting more data than ever before. Business organizations are investing in big data and machine learning projects. However, most of these projects are predicted to fail. One research suggests key obstacle is lack of understanding of how to use data analytics to improve business value. Here's the problem statement. One way to improve business value would be finding and solving right business problems. However, finding and validating business problems is not an easy work. In other words, the problem is difficult in finding and validating business problems. Specifically, first, difficult in finding business problems hidden in the data. Second, difficult in figuring out what kind of data would be correspond to the problems. Third, difficulty in understanding of how important the data would be to the problems. Lastly, difficulty in validating the problems. In the bank world, customer churn, where customers leave and join another service provider, might be a problem, which could hinder bank's goal increasing profitability. In our empirical study about bank customer churn, we could not find much evidence about dissatisfaction among loyal customers and churn customers. Can goal orientation and machine learning help find and validate business problems? If yes, then the next question is how? To tackle these problems, we present Metis, a goal-oriented problem hypothesis validation method using machine learning. Here, we present Metis framework a little bit progress research. First, the Metis framework consists of the following components. First, domain-specific ontology. In this paper, we examine the banking domain ontology. Second, Metis ontology, essential modeling concepts, relationships, and constraints. Third, semantic reasoning formalization, such as validation of problem hypotheses, decomposed with and/or relationship, and deriving contribution type between problem hypotheses, and score calculation formula of problem hypothesis. We will not discuss much of this reasoning formalization due to time constraint. Fourth, Metis include Metis process. To give general ideas of how Metis works, first we present the Metis process. The Metis process includes 4 steps. Step 1 is model business goals and problems. Here, business needs and obstacles are input to this step. Then step 1 output business goal models and hypothesized business problems. Next, step 2 is acquire new data or identify existing data. For the hypothesized business problems, step 2 output data features corresponding to the problem hypothesis and extract a relevant dataset. Then step 3 is detect feature importance. Utilizing machine learning and explainability library, this step detect feature importance value. Last step 4 is validate hypotheses of business problems. Based on the feature importance, we evaluate the hypothesized problems with quantitative and qualitative reasoning method. The output of step 4 is validate business problem or invalidate business problem. Here you can see the domain-specific ontology, domain-specific banking ontology. To understand the banking domain and customer churn, we examine a set of banking concepts and their relationship. For example, here banks provide important services such as financial advising, cash withdrawal, issuing credit card, and issuing checkbook. Some quality issues such as lack of immediate attention, lack of pleasant ambience, or not enough parking spaces might lead to customer churn. Here is Metis modeling concept and relationships. Some key concepts are soft goals, problem hypothesis, machine learning, and data features. And key relationships are contributions and validated or invalidated. In Metis, a soft goal is defined as a goal which may not have a clear-cut criteria. A problem is defined as a phenomenon which negatively contribute to goals. A problem hypothesis is a hypothesis about a problem which needs to be validated or invalidated using machine learning. Based on this concept and their relationships, Metis can help model essential concept, relationship, and some constraints in machine learning projects. Metis also helps prevent validated incorrect problem hypothesis. Here is one use of Metis modeling concept. In the middle part, in the class level, in the figure, suppose bank has a goal of retaining existing customers. This can be modeled as instance of a goal. However, customer churn could be a problem to achieve the goal. Customer churn can be modeled as an instance of problem. Here, the long distance to residence might be a potential problem, which could lead to customer churn. Long distance to residence is an instance of problem hypothesis. Like this, in modeling goals and problem hypothesis in customer churn, you can use the Metis modeling concept and relationships in meta classes and token level. In the next slide, we'll explain the 4 steps of Metis process in more detail. Step 1 is model business goals and problems. In the banking example, here please look at the top part of this graph. The high-level business goal is increased profitability. This goal can be decomposed to increase revenue and increase profit margin, non-functional soft goals. We can decompose the non-functional soft goal until operationalizing soft goal. Here, one of the operationalizing soft goals is retain existing customer. Then we consider potential problems which might negatively contribute to the goal. In other words, in the context of the captured business goal, we explore potential problems. Here we consider customer churn problem. Like the goal refinement, we can refine customer churn problems in order to iterate data features in a dataset. Here we have 14 leaf level problem hypotheses. Some problem hypotheses include lack of facility to pay bills, long distance to residence, and lack of pleasant ambience. In this hypothesized problem model, the validity of this potential problem is not known yet at this point. Next, step 2 is acquire new data or identify existing data. Here, let's consider one problem hypothesis. P1, long distance to residence might contribute to customer churn. First, we define an operational criterion and identify operational features of this problem hypothesis. Here, we could consider differently about the long-distance radius. For example, we can consider the problem hypothesis in terms of satisfaction score in a customer survey, or miles by car, or physical distance, or minutes by car, or time. After we communicate with the bank step and machine learning project step, we select satisfaction score as the operational criteria. And then we use long distance tolerance as the operational feature. Next, we model the problem hypothesis as a class in UML. Then we map the operational features to data features in a database schema. We use the cosine similarity as a relevance measure adapted in information retrieval research. Then we build the database corre or BigQuery with the identified data features and classification label. And we extract dataset by learning the BigQuery. Step 3 is detect feature importance. First, we train, test a supervised prediction model to encode knowledge about features. We utilize classification algorithms such as logistic regression, decision tree, support vector machine, and random forest. Next, we select machine learning model showing the best accuracy. Then we build an explainability model to decode knowledge about features. The machine learning model is as input to the explainability model. Among the several explainability models, we applied the Churn model, which gives intuitive and consistent feature value. Last, we detect feature importance for the data features. The feature importance value has the positive or negative side and rate of contribution. It means degree of importance. Here in the figure, I1 to I5 represent feature importance value. Step 4 is validate hypotheses of business problems. First, in the problem hypothesis model, in the right side, we update the contribution type and a leaf node label based on the feature importance value. For example, here I1 is 1 plus 1.95. So the contribution type becomes S plus, sum plus from the contribution type formula. Next, P1 becomes 0.39 from the score calculation formula. Then we validate problem hypothesis. Here in the below side, in the graph, P1 is selected and checkmarked among P1, P2, P4 as it has highest value among them. Then PB is checkmarked and then PA is checkmarked by here or contribution. PB or PC is checkmarked, then PA is checkmarked. Here we use qualitative reasoning method. Next, we present experimental result. Here we show the analysis result of bank Churn dataset. The dataset consists of customer information and feedback information about bank services and facility. Customers gave 10 to 0 points for the very satisfied service to very dissatisfied ones. For analysis purpose, customers who scored 0 to 4 were treated as dissatisfied customers. Here we analyze 3 data features: long distance radius, lack of immediate attention, and lack of pleasant ambience. From the figure, we can see most customers remained loyal, although they show some dissatisfaction about service and facility. This analysis does not show clear evidence of why some customers deserted. For example, many customers did not complain about long distance radius. Next, to get a better idea of potential causes of customer churn, we investigate feature importance. Based on the identified features and classification label, we built prediction models, including linear regression, sub-vector machine, distance tree, random forest, and gradient boost distance tree. Here, a gradient boost distance tree shows the highest accuracy, 84%. Next, we detect and extract feature contribution by utilizing explanatory model, shape library. Here, in the upper side of the graph, we show the one channel list price. The channel showed very dissatisfaction for the distance to residence. Here, the value is 0. And then some dissatisfaction about comfortable sitting. The score is 3. Here, if the width is wider, it indicates higher contribution. In the lower side of the graph, the features in the higher position indicate higher importance among the features. We see that distance to residence and comfortable sitting, error in passing are important factors. Next, we validate problem hypothesis with the feature importance value. First, we apply quantitative semantic reasoning. In the graph, we validate long distance to residence as it has highest value among the 6 problem hypotheses toward for facility. Next, we apply qualitative semantic reasoning. Over some plus satisfying contribution, if the long distance to residence is satisfied and some plus is satisfied, then poor facility is satisfied. Then the customer churn is satisfied by all contribution. And over the great satisfying contribution, if the customer churn is satisfied and the great contribution is satisfied, and the retained existing customer is likely to be denied. Here, hypothesis of poor facility problem, including long distance to residence, is likely to be a reason for customer churn is validated. However, in the previous customer churn dataset analysis, customer did not complain about long distance to residence, where it seemed to be difficult to catch the above insight. Now we discuss later work. Goal orientation is very helpful for stakeholder goal analysis and problem abstract analysis. However, there's not much work about potential problems using machine learning, and it's difficult to understand the validation of goal models using statistical hypotheses. On the other hand, machine learning is very helpful performing prediction from large data sets and good at finding underlying patterns. However, there's not clear relationships among goals, low-level problems, and data features. We feel that Metis framework utilizing an end-to-end explicit and formal approach provides traceability among business goals, problems, problem hypotheses, machine learning, and big data. Here is a conclusion and future work. In this paper, we presented Metis method that uses machine learning to validating hypotheses of business problems. Metis helps understand end-to-end relationships among important business goals, problems, machine learning, and big data. We feel that Metis can help improve business value by discovering and validating potential problems hidden in the data. 3 technical contributions have been presented. Specifically, first, we present the Metis ontology, explicitly and formally describing modeling concepts. Second, we present a set of formalized validation rules for reasoning about problem hypothesis validation. Third, we present machine learning-based approach to extract a root cause hidden in the data. Limitations include, first, interfeature relationships, shape such as and or are not supported by the current shape library. Second, it's not clear whether the experimental result would be consistent for other machine learning algorithms and explanatory libraries such as LIFE. Research challenges would include more systematic and explicit mapping methods from problem hypothesis to features, and exploration of possible business action that could mitigate problems. Here is a future work. We plan to conduct optional experiments with a larger dataset and to test with more diverse machine learning and exploratory models. And we also plan to investigate solutions for encoding end-node relationship in the dataset. Lastly, we plan to build a full-fledged tool assisting novice users in the Metis process. Okay, this is the last slide. Thank you very much for your attention. If you have any questions, please contact me by this email address. Thank you.